Okay, guys, so the next part of the colligative property is going to be the osmotic pressure. So osmotic pressure basically is when dissolved particles start moving through different membranes, right? So let's talk about the semi-permeable membrane. The semi-permeable membrane means that water can pass through it, but molecules and ions cannot. So semi-permeable is only water can pass through that membrane. Okay. No molecules or ions. Right. And so in this example, what you see is kind of like the reason osmotic pressure is like very important is because in our cells, our bodies, they work through osmotic pressure, our blood cells and everything that we see. So here we have a cell membrane, and through the cell membrane, we have the interior and the exterior cell, right? But the ions can't pass through it. Only the water passes in and out through that cell membrane, trying to keep us healthy and steady, right? So water is very important in everything that we do, and we're going to talk about why it's important to be nicely hydrated and those kind of things as well. So osmotic pressure, water moves towards the more concentrated solution. So on osmotic pressure, water moves towards the more concentrated solution. Okay. So let's go ahead and look at some examples of this. So here we have two containers. One container has some ions in it. The other container only has water in it. So because this first container has less water, right? It's less concentrated and it has more ions though. Less concentrated in water, but more concentrated in salt, right? It has a lot of high salt concentration. The water is actually going to leave this container here, and through osmotic pressure, it's going to move to the more concentrated. So this one's more concentrated, right? And it's what it's trying to do. It's trying to balance it out. So this part gets less water, this part gets more water, but it's less concentrated now. So what I want to do is I want to look at osmotic pressure when it relates to our blood. So the osmotic pressure in our blood cells, so this is what my three little circles represent. My first one is going to be hypertonic. The next one is going to be isotonic. And this one is hypotonic. So in this first one, what we see is shriveled up cells, right? These cells are shriveled. Why do we think these cells are shriveled? Well, inside of here, we're going to say there's water in all of these. Okay, so let's give them a good little blue tint. But what we're actually looking at is going to be the salt, because human blood cells are made of salts and of water. So we're made of salts and water. So in this one, we have shriveled up blood cells with no water inside of them. The reason why this happened is because this here outside has a high concentration. So it has a high concentration of salts. So it's a high salt concentration. And that's going to cause the water from the cells to seep out in order to try to reduce that concentration. And in turn, though, the cells shrivel up. Okay, so this usually happens when we are dehydrated in ourselves, right? And we see it in our skin. It looks a little bit wrinkly. It doesn't look as full. And then we start drinking water and we could immediately feel the difference and see the difference in our skin. So hypertonics, we have a high salt concentration in our body, and the water in our cells is trying to leave to compensate for that, causing it to shrivel out. So the water is exiting. So H2O exits. Water leaves the cell, causing it to shrivel. Now let's look at isotonic. In an isotonic, you'll notice that the cells are actually very nice. They're very nicely looking, no issues whatsoever. They're living happy in their forms right there. And that's because in this one, water goes in and out equally. So we have equal concentrations, or about equal concentrations of salt in cell and out of the cell. Okay, so they're equal concentrations here. So it's about equal. I'm going to put equal. And then if we look at this other one, you'll notice that they're kind of ballooned up, right? So they're super ballooned up. And when they get super ballooned, what had end up happening is that they actually burst. Okay, and if it bursts, it's going to be releasing water as well. But the reason it's bursting is because water, H2O, from here, from this membrane, is going into the cell. And the reason that is happening is because inside of the cell, you have high concentration. So here you have a high salt inside of the blood cell. So water goes into the cell. So it increases the water flow into the cell, causing it to balloon and explode. Okay. So here we go, the 3 different types of the human blood cells and the 3 different things that can actually happen when we're not properly hydrated, or when we overly hydrate, right? So excessive amounts of water, we dilute. The problem with this is we could dilute actually the electrolytes inside of your system. And when you dilute the electrolytes inside of your system, that's going to create a lot of other health issues. So at times we go to the doctor's office and they give us the liters of water, or not water, but IVs, that saline solution. And that saline solution is probably like a 0.9. I don't remember what we talked about earlier, but it has a low concentration of sodium chloride. We don't want to put too much sodium chloride inside of someone's body, because that could also lead to hypertonic, right? So, and then too much water, vice versa. We want a good amount of water flowing in and out of our bodies. All right. And in this last example, what we see right here is just like, how do we calculate this involving solutions? So in one container, we have sodium chloride 1 molar, and the next container, we have calcium chloride 1 molar. Well, which one has the higher osmotic pressure? Well, we learned earlier that osmotic pressure, just like freezing point and boiling point, it's a colligative property, which means it does not depend on what it is, only on how much you have. And we have to look at the mole values of what we have. So in the example, this is sodium chloride, and it's connected to another container containing calcium chloride. Here we have sodium and chlorine. Oops, negative. Positive 1. So we have 2 moles. And here we have calcium chloride, which is calcium, plus 2 chlorines, which gives me 3 moles. So therefore, the calcium chloride is more concentrated. So my solution is actually going to flow like this. My water is going to flow from this container into the calcium chloride container, because the calcium chloride container is the more concentrated container. So we're going to have that water flow into that to help make it less concentrated and reach some sort of isotonic kind of pressure. All right, in summary for this one, freezing point, boiling point, and osmotic pressures, right? They all depend on the quantity of particles that you have. So the mole values of your particles, not on what it is. It could be sodium chloride, magnesium chloride, calcium chloride. It doesn't matter which one, which salt you have. It's only how much of that do you have versus, actually there's no versus, it's just how much do you have, right? The one that has the most increases the boiling point and decreases the freezing point, and it increases the water flow going towards it. The more particles creates more electricity, more ions, all that great stuff. All right, so that ends the osmotic pressure one. And we're going to quickly go into reactions in solutions. And we have 3 reactions in solutions: precipitation, acid-base neutralization, and metal displacement. So in precipitation reactions, we've seen all of this in, I believe, chapter 6, right? We talked about types of reactions, and then a little bit further on. So 2 solutions combine together to form a product, a solid product nonetheless. And we could describe the precipitation reactions in molecular equations, complete ionic equations, and net ionic equations. So in a molecular equation, basically is when we write something out. And I'm not going to use this example. I'm going to use like a simpler example just to kind of help out. Actually, you know what? No, let's just use this one because it's already here and I don't want to mess up. All right, so silver nitrate, aqueous, plus potassium chloride, aqueous, creates silver chloride, solid, plus potassium nitrate, aqueous. Now, how did we know it created a solid versus not a solid? Well, it's going to all depend on the solubility, and that's going to be on the solubility rules, right? So solubility, you could just look up a chart, or you could try to memorize all the rules. There's a lot of rules out there. But the majority of things are soluble. The majority of things are soluble. Nitrates, all nitrates, right, are soluble. As you can see, all soluble. Chlorates, perchlorates, acetates, all soluble. Now, when it comes to chlorine, they're not all soluble. Chlorine is soluble in almost everything except for lead and silver. So chlorine, almost everything except for lead and silver. And the same goes for the rest of the halogens, right? You'll notice that you have bromine and iodine, same thing. They're not soluble in silver and they're not soluble in lead. Those are our heavier metals that we have right there. So silver chloride, here's chloride and here's silver, it's not soluble. So that's how we ended up with that solid. Okay. Now, when we want to write the complete ionic equation, we're basically going to break everything apart that is aqueous into its ion form. So I'm going to start over here just because of space. I have silver nitrate, so silver is a +1, plus nitrate is going to be a -1. These are all aqueous, and because I don't have space, I'm not going to write the word aqueous on there. Okay. We have potassium +1 plus chlorine. There's only 1, so -1. And this is going to give me silver chloride, a solid. And let me actually put that in a different color so we can notice that this is a solid. That means it did not dissociate inside of water. It is our precipitate that was created. Plus the nitrate ion. Okay, and you know what? No. I was going to put parentheses in aqueous, but that doesn't work because all of these this one is solid. All right, so net ionic. In a net ionic equation, remember, we're going to get rid of the spectator ions. So no spectator ions for the net ionic equation. And the spectator ions are the ions that had nothing to do with the creation of the precipitate. So my precipitate is made out of silver and chlorine. So if it's not silver or chlorine, I'm going to get rid of it, or a solid attached to silver and chlorine, I'm going to get rid of it. So I have silver here. I need nitrate here, and it repeats over here by itself. Get rid of it. Potassium is here, and it repeats by itself right there. I'm going to get rid of it. Those are all my spectator ions. So now I'm going to rewrite my net ionic as silver +1. I have space now, so that's aqueous. Let me use a different color. +1. And then it's aqueous. Plus chlorine, -1, aqueous. Gives me silver chloride, solid, plus nothing else. There's no plus. That's it, because everything else was removed. And this is my net ionic equation for the creation of silver chloride. And remember, from this we could go into redox and whatnot, but we're not doing redox. All right, so from precipitation reactions, we also can do acid-base neutralization reactions. And acid-base neutralization reactions, basically you're combining an acid like hydrochloric, acetic, sulfuric, all these acids. You're going to combine an acid with a base. Sodium hydroxide, maybe, that's the most common one. Ammonium hydroxide. So, and any acid and base combination is always going to produce a water and a salt that has that anion inside of it. Okay, so it's going to produce a water and a salt. Salt basically means an ionic compound, which is a metal plus a non-metal. And that's going to there's a little bit more to it, but just in our kind of level, that's the best way to try to memorize what is a salt. It is going to be a metal plus a non-metal, and that's going to create our salt. All right. So in this one, we have hydrochloric acid plus magnesium hydroxide. Magnesium hydroxide is probably something that we drink to help our stomachs out, right? So acid plus a base is going to produce water plus magnesium chloride, right? And that's quite simple for us. So it's acid, any kind of acid. In this case, we used hydrochloric acid, and then a base. This one uses magnesium hydroxide. So you could say magnesium hydroxide. I'm going to do sodium hydroxide only because it's a 1:1 ratio. Makes it super easy. H2O plus. So hydrogen combines with this OH, and sodium combines with this chlorine. Sodium chloride, right? Aqueous, and this is a liquid right there. And they're all a 1:1 ratio in the example that I used right here. Acid plus water or acid-base neutralization reactions are also known as double replacement reactions. So the only difference is that this produces water and a salt. We always know what it's going to produce. So it is a type of double replacement. That's better said. A type of double replacement reaction. And that's the one we call the swingers because they switch partners. All right, and last but not least, we have metal displacement. So metal displacement reactions is basically going to be like our single replacement reaction. So metal displacement is like our single replacement, the home wrecker. Single displacement reaction. Okay, like I said, the home wrecker. And we use the activity series, if we recall, in order to figure out if that metal ion is going to react with the metal form. And the activity series, just in case we have forgot, looks something like this, where the lighter atoms are, or the lighter elements are on top, and the heavier elements are at the bottom. The heavier elements are least reactive, the lighter elements are the most reactive. You could only replace a metal that is below you. You cannot replace a metal that is above you. With that being said, let's say calcium, right? The calcium, I throw some calcium metal inside a solution of lithium chloride. Can calcium replace the lithium inside of lithium chloride? No, it cannot, because lithium is lighter than calcium and it's above calcium in the reactivity series. Now, the only thing you guys have to watch out for in the reactivity series is hydrogen itself. So you notice that hydrogen is down here, and that's because of the differences in how it reacts with acids and whatnot. So just pay attention to hydrogen is the only one that doesn't fall with the heavy versus not heavy kind of rule. Okay. So metal displacements, we have to look at the activity series of the metals, and basically is, can one metal replace another metal in the reactivity series? And if it can replacement, you have a reaction. If it cannot replacement, you're going to write no reaction. So when I said, the example I said is, can calcium solid replace lithium in like a lithium chloride aqueous solution? And in this case, when we saw the reactivity series, or the activity series, we saw that it cannot. So this is a no reaction. and R is what we were using in our lab to show that there was no reaction. In the example that we have here, you could clearly see that they do have a reaction that occurs. All right. So in summary, precipitation reactions are double displacement reactions, and they give a precipitate. That's how we know we have a precipitate type of reaction. Acid-base neutralization reactions are going to give a water and a salt, and a metal displacement reaction is a single displacement reaction, and it's going to basically just give you a metal by itself and a combination, as you can see right here. But you're going to have to look at the activity series to make sure that it can be replaced. All right. Last but not least is going to be our solution stoichiometry. So solution stoichiometry is basically math conversions using solutions, right? We just finished gas stoichiometry, so now solution stoichiometry. So we should have a good hand of this, like knowing how to do and manipulate our units now, right? So we're gonna do from we did solution and volume, so now we can go solution volume to moles. We can convert moles to anything that we want, basically, even to moles of B, a different compound, right? So we're gonna be converting. Start with the first one. Silver and chlorine ions react as shown in the following ionic equation. Based on this, how many grams of silver chloride precipitate would be produced if 10 milliliters of solution containing a 0.0023 molar chloride ions react with excess silver? Go ahead and read that on your own. All right. So silver and chlorine, they're going to react aiming 1-to-1 ratio. We have 0.0023 molarity, right? And if we recall, molarity is moles per liter. We want grams of silver chloride. So what are the different things we have to do? So let's look at this example. I'm going to actually use a different page to write my example because I don't want to mess this one up. All right. So in our example, we're going to see that we have silver chloride is what we're looking for. We're looking for grams. So we want grams of silver chloride. Okay. We have 0.0023 molarity of chloride ions. Well, if we look at this chart, we have molarity of chloride ions. So that's somewhere over here, right? That we have to get to moles of B so we could get to moles of A. Okay? And once we get to moles of A, then we could figure out the grams of A. So we're going to have about 3 steps, I believe. All right. So we're going to go from molarity of the chlorine ion to moles of the chlorine ion to moles of our silver chloride to grams of the silver chloride. Okay, so these are our steps, and now it's very important for us to write our units down so that way we don't mess up when actually doing this problem. So I haven't done this problem yet, so I'm kind of excited to try it out and cross my fingers. I hope I don't mess up. All right, here we go. So molarity, always start with your given. My given is 0.0023. And remember, molarity is the same as moles per liter in inches in 1 liter. And this is of our chlorine ion. Okay. Now, let's see what else it says. So I want to get rid of moles. Sorry, I want to get rid of liters so that I could end up with moles. And the only way that I could get rid of liters is to figure out the volume, right? And here it says that we use 10 milliliters of the solution. 10 milliliters of the solution. And 10 milliliters can be converted into liters by using our, I forgot the name. It's not any conversion factor. And so in 1 liter, there's 1,000 milliliters. Okay, so that basically means we're going to take 10 and divide it by 1,000. Okay. And figure out what this one is here. And according to this, it actually already did our math for us. And so that's going to be 0.01 liter. Okay, that's what that turns out to. Okay. And in the bottom right here, it's just a 1. Just the 1. Most people freak out and go, oh my God, I don't know what to put here. And they start putting random stuff in there because they feel like they have to put something in there. Just put a 1. That's it, right? A whole number is just a number over 1. All right, so let's see so far. Liters can now cancel out with this liter. Milliliter can cancel out with that milliliter. So we're good, right? We have moles of chlorine, and that's what we want. So we're here now. We're going to go from here to moles of silver chloride. And the way we're going to use this one is by the balanced chemical equation. So the unit I want to get rid of, this one, is going to go at the bottom, and the unit that I want is going to go at the top. So I have moles, and I'm going to write moles of chlorine at the bottom, and I want moles of silver chloride. And according to the balanced chemical equation, everything is a 1-to-1 ratio. So I'm just going to write a 1-to-1. So now moles of chlorine cancels out with moles of chlorine, and I'm left with moles of silver chloride. I got one more step, and I'm going to go from moles to grams. And the only way to go from moles to grams is by using the molar mass. Okay, so I'm going to get rid of this mole and bring it down. 1 mole of silver chloride. And then I'm going to need the molar mass of silver chloride. And I don't have a periodic table with me, so I'm going to Google p-table and figure it out. Okay. So we look at here, silver is 107.87. So silver is 107.87, and chlorine should be 35.45. We add those together, what is that going to be? 2, 1, 8, 9, 10, 11, 12, 13, carry the 1, and that is going to be 12, 13, carry the 1. Okay, 143 and 32. You know what? I don't trust my math. Ooh, ever since all that brain fog happening and whatnot, I do not trust my mathematics. So let me put in a fancy dancy calculator. I got 143.32. Okay, good. I did well. 143.32 grams of silver chloride. So now this mole can cancel out with that mole, and we could just do our mathy math, right? Now, some of you guys will go, oh, this is a little bit too messy, and you don't know what to do because it's messy. Well, we could always rewrite it to make it less messy, right? Get rid of everything that we don't need so that we could see the problem a little bit better and not be as confused. So 0.0023 over 1, I'm not going to write that, times 0.01 times 1 divided by 1, not going to write that, times 143.32. Okay, now we could take our fancy dance calculator and do the math. So 0.01 times 0.0023. And I got 3.29636 times 10 to the negative 3. Now, we always know that we don't write everything that we see on a calculator. We look at the significant figures. The problem gives me 3 sig figs here and 2 significant figures there. So my answer has to be in 2 significant figures, which goes right there. So I'm going to write this as 3.3 times 10 to the negative 3 grams of silver chloride. I have no idea if I did this correct. So let's go ahead and take a look. All right, so our molarity is there, and we're going to be converting, right? So they're taking this into smaller steps. I don't like doing that personally. I like putting everything together because it makes the math calculating a lot easier at the end. All right, so they took their molarity and they multiplied it by the liters, which is what we did here, in order to get rid of the liters. And that gave them moles of chlorine. And now for moles of chlorine, we're going to go to moles of silver chloride using the balanced chemical equation. So this here, we divided by the volume. And that's how we got rid of the liters and ended up with moles. From here to here, we were using the balanced chemical equation, right? The coefficients from the balanced chemical equation. And from here to here, the molar mass from the periodic table. Right? So they got 143.32, just like we did right here. So now they're taking that number that they obtained, doing the 1-to-1 mole ratio from the balanced chemical equation, just like we did, and multiplying it by the molar mass, just like we did. And they got 3.3 times 10 to the negative 3 grams of silver chloride. We are correct. Give ourselves a pat in the back. All right. I'm going to put this back up here, and then we're just going to quickly talk about this. So the uses of masses of precipitate to determine the concentration of the reactant. That's all we're doing. So the concentration of ions inside of the solution, the only way to know that is by actually doing some calculations. So in this case, there is lead plus iodine, and this is the ionic equation, as you can see, the net ionic, because it creates lead iodine solid in here. So there might be some solid somewhere in there. I don't know. So how do we figure out? Okay, using a gravimetric analysis. Okay. 1, measure the volume of your solvent. 2, you're going to precipitate the ion, right? So here now we have some ion that precipitates. How do we know how much we have of that solid? Well, our most scientific method is filter and dry the precipitate. Now you're going to have to do a couple of washes and whatnot while you're filtering in order to make sure that you obtain all of it from inside of here and all of it from in here. So a couple of washes per se. And then you measure the dry precipitate. And that gives you the grams. Quite simple, right? So this is gravimetric analysis. Okay. This is another problem using our solution stoichiometry. Okay, I want you guys to actually go ahead, pause this one, and try the problem. I'm going to show you guys the answer, but pause, try the problem. Have you paused it? I don't think you have. All right, let's see how you did. Hopefully now you've finished unpausing it, and you're going to try the problem out. So says the concentration of sulfate ions in a solution may be measured using a precipitate reaction with barium chloride. The net ionic equation for this reaction is the following. So you have barium plus sulfate gives you barium sulfate solution. So two aqueous mixed together, creating a precipitate. You need to measure the sulfate concentration in large drum containing aqueous sodium sulfate. From the drum, you measure a 0.2 liter sample and react this with excess barium chloride. So that means don't worry about the barium chloride, right? Which ones you're limiting. The reaction produces barium sulfate as a precipitate, which you carefully filter and dry. The barium sulfate precipitate has a mass of 0.309 grams. What is the concentration in molarity of sulfate ion in the drum? Okay, so now we're going to go from grams to moles, from moles to moles, and from moles to our concentration. So we're going to take different steps, right? So the grams of barium sulfate, use the molar mass in order to turn it into moles of barium sulfate. Use the balanced chemical equation to go from moles of barium sulfate to moles of your ion, which is your sulfate ion. And here we could see it's all a 1-to-1 ratio. And we end up with moles of our sulfate ion. But we're not done because this wants to know the molarity. So all we have to do, we know that molarity is moles per liter. Take your moles and divide it by your liter sample. And we end up with our molarity, our molarity of sulfate ions in the solution, right? So these are the steps that we took for it. I hope that you guys were able to actually figure that out. If not, go through this process step by step until you do. All right, so when we're looking at our stoichiometry problems, we have this beautiful flowchart that I want you guys to create with me. So from moles of A, we could actually figure out the solution volume using molarity, which is basically moles per liter, right? We could figure out the gas pressure or the volume using the ideal gas law, PV equals nRT. We could figure out the number of atoms using Avogadro's number. We could figure out the number of moles of a different substance using the balanced chemical equation. So the coefficients. And we could figure out how many grams we have using the molar mass. So this is our solution stoichiometry flowchart. And this part here just repeats the same thing again. So you could actually rewrite it if it helps you, so that you could go, okay, if all of these are A's, and then write your B's down, so you could go from this to this, from this to this, right? It really does help to always look at a solution stoichiometry flowchart when you're trying to solve a problem, so you don't accidentally miss a step. Oh, and here's another problem. It's saying, given the number of moles, how many moles of H2O are produced using this? So you're going to go from moles of A to moles of B, and that's it, using the mole-to-mole ratio. That's it, mole-to-mole ratio. That's how you figure it out. And you get the mole-to-mole ratio by the coefficients from the balanced chemical equation. All right, guys, I really hope that this that solution stoichiometry, that you guys were able to get it. And note that it's not really hard at all. It does take some practice, okay, when you're doing your problems. Oh, here's another one. It's actually kind of cool. So now this one relates to gas. Why don't we give it a try? Why not? We'll end with a little bit of solution stoichiometry here. Okay. Calcium metal reacts with aqueous hydrobromic acid to produce calcium bromide and hydrogen gas, as shown in the equation below. What volume of 2.5 molarity? Okay, so my molarity is 2.5 moles per liter of hydrobromide. Okay, and I'm looking for the volume of this. So the volume of the HBr, I don't know it. Required to produce 200 liters of hydrogen gas. So this is all my ones. And I want to produce 200 liters of hydrogen gas at a temperature of 298 Kelvin and a pressure equal to 1.20 atmospheres, ATMs. All right. So let's get going. According to this, we're going to go from volume of H2 to moles of H2 to moles of hydrobromic to volume of hydrobromic. Okay. So following our chart, and the reason why is because this is the information that we were given more of, and we're given less of this. So we're going to go from here to here. This is our initial, and this is our final, right, quantities that we have. So always start with what you're given. So we're given our volume of H2 as 200 liters, okay? And with that, we could figure out the moles of H2. So using PV equals nRT, which is the ideal gas law, So I have PV is equal to nRT. We have volume, but we want moles. And if we recall, moles is the N. That is the N. So I'm going to divide everything by RT. So in this first step, in order to get the number of moles, I have to get PV divided by RT. That's my first step that I'm going to have to take. So my pressure is 1.2. My volume is 200 liters. My R is going to be 0. I believe it was, actually they wrote it down. So my R is 0.0821. And my temperature is in Kelvin, so I don't need to convert anything, 298. Okay, so this is step one. After step one is done, then I could get moles of H2, right? So, and I'm going to do that by using the balanced chemical equation. So from this point, I do go to moles of H2, and from the balanced chemical equation, I see that I have 1 mole of H2 present. All right, let's see where we go from here. All right, I ended up with 9.81 moles of H2 here. And I want to get rid of my moles of H2 using the balanced chemical equation to get moles of HBr. So that's actually where I started messing up. So moles of HBr, because I already got moles of H2 here. So the moles of H2 calculated was 9.81 moles of hydrogen. I could take my moles of hydrogen using the balanced chemical equation. HBr, we have 2 moles of that. And hydrogen, we have 1 mole of hydrogen gas. So this is the answer to that. 2 over 1 is the same as 2. And then in the next step that we're going to do, we're going to take our moles of HBr and we're going to obtain the volume of HBr by using the molarity, right? So remember, molarity is moles per liter, and we could easily switch that around. So our molarity was given to us as, where did we write it down? 2.50. Okay. So I have 2.50 moles in 1 liter. And I'm going to write this down as, well, just 1 over 2.5. And then that allows us to easily do our calculations. And we end up with the volume equal to 7.85 liters of our hydrobromic. Okay, so all of these steps were taken. The most complex step for us to actually understand about this one is using this section, because we forget that gases can actually relate to our stoichiometry, and this is one of the most common things that we forget. So if we have pressures and temperatures, grams, you could take grams and convert it to moles and then plug it into here as well. So if you get your pressures, temperatures, and you have solutions going on, somewhere in there, you're probably going to use PV equals nRT to solve that problem. All right, now we're done. I really hope that this helped you guys some. And remember, if you have any questions on this, feel free to contact me. Write your solution stoichiometry flowchart. It really does help. All right, ciao, you guys.